Hello, my name is Conny Andersen, and I work with LSA software engineering. And in this presentation, we're going to go through an overview of commit queues, Nano services, and LSA with focus on performance. NSO transactions is like the core of achieving performance, knowing the details or some details at least of NSO's transaction manager and the different steps that NSO goes through to for example, map from a service to device configuration and then update devices with that configuration. So it starts typically with restconf, yang patch, for example, netconf, editconfig, or CLI config. Several of these might be done in parallel, and that would be the best use case where you have, for example, one service instance mapped to one device or network elements, which will then be updated by the service instance. So you might have like three, four, or five, several of these being done in parallel. What will happen then with NSO is NSO will go through a read-write step. And this is where NSO calculates the minimum diff of the configuration, what's existing in CDB and what's actually going to be updated, and takes that minimum diff and applies that to CDB later. Next step would be transaction hooks, where you have some pre-validation for the resource-facing service. And you have the service manager create, where your create code might be Python code, Java code, Erlang code, maps then the service to the device might be a template or a template plus code that does that. Then you have the validate step where you have Yang validation. It could be a must statement with XPath expression that does some things, and you can see the details of the XPath expression running in the XPath trace if you turn that on. And you have custom validation where again, some of your code, Python code, for example, might be running to validate some things before you move on. All these steps, by the way, you can use, as I will show later, the progress trace to get the details of what NSO is doing, going through this from the read-write phase to unlocking the transaction. After the validate phase here, the transaction will be locked. NSO will check for conflicts. If the conflicts between these multiple concurrent transactions running here, the transaction that had the conflict will start over and try again. And then while this lock is being done here or happening, CDB will be updated, and the NED or the network element driver prepare and the commit queue prepare will be done by NSO. And then the commit where CDB would be updated, the devices would be updated. If you have the commit queue enabled, the devices will be updated there, and then the unlock will happen. If you don't use commit queues here, of course, then the transaction unlock will be happening when the devices actually replied and said, okay, I got the configuration updates now in my database, for example, and here you can continue. But if you had commit queues running here or using commit queues, the transaction would be unlocked when NSO has placed the configuration update in commit queue, and then the commit queue will then take care of updating the device. If we take a look at performance then, with the transaction manager here in NSO, we want to have concurrent transactions going in here. Typically, we want to design our service in a way that each service instance maps to one device or one network element. And this can be done by having, for example, your service declarations inside a list in your Yang model, which is typically what you do. And then that will be mapped to a device. This way, we can have several RESTconf, for example, or netconf or CLI commits being done concurrently, where each one will update basically one device then, where we enter transaction manager concurrently, go through the steps, and we'll take less time in that way, and we'll go through how you can do that later in this presentation. What you still want to do, even though you're running several transactions in concurrently here and utilizing the processor that you're running on the multi-core processor, for example, is to minimize the time taken for example, a service create where you have your Python code, Java code mapped then from a service to device configuration. You want to minimize the time spent with Yang validation, for example, must statements and XPath expressions being executed. You might want to check out the XPath trace log if you see in the progress trace, we'll take a look at later, why this is taking so much time. You want to make sure that your custom validation code, which might be your Python or Java code, runs very fast as well here, or as fast as it can. So that then when the transaction lock is taken, then these transactions, as I mentioned, will be going through this step one by one. And here you want to make sure that the commit then that happens to CDB and then to the devices, that takes as little time as possible. And one way to do that is to commit queues instead of to device themselves. I mean, device commits can take quite some time. And if you don't have commit queues, this step will include the step it takes to update the device, where the device then has to reply back to NSO that, okay, I have entered the configuration to my database, you can now move on, and the lock will be released then. If you instead commit to a commit queue for that device, where the service instance maps to the device and device configuration will then be committed to CDB and to a commit queue, the lock will be released as soon as the commit queue has been updated. Let's look at transaction concurrency here. Here you have a picture with some lines. These lines here are representing basically what we saw in the previous picture, the transaction manager. Same colors. We have a little bit darker blue for the service creation, the validation step in green, and then we have the critical section in orange, and we also have a transaction lock weight here, which is the gray area. So if you have one transaction updating, for example, 3 service instances that maps to 3 devices, that can be done, of course, in this way, where it will take some time then to update all 3. That will not be done in parallel in that case. If you do that, you do the service create here one by one, and then you do the validation one by one, and then you have the critical section being done one by one again, and the devices will be updated. What will be done in parallel here will be the updating of the devices. And you can, in this case, since you only have one transaction going, you know that there will be no other transactions going here concurrently, then you can just skip commit queues and commit to the devices, since you don't have anyone waiting for the lock over here. And NSO will still paralyze the updating of the devices, but the lock won't really be released until the slowest device have actually replied or said, okay, I got the configuration now. So this is a simple option here if you want, if you don't care so much about the wall clock performance and how long this takes, and you don't really have that many transactions going concurrently. So this can be what you want to do done. So what you can see here represented is a multi-core processor, and this kind of transaction, you would run it just on one core, everything being done one by one. On the other hand, if you want to optimize for wall clock performance and you want to do this fast, let's say you have 3 transactions, you can then parallelize those 3 transactions, multiple, for example, REST conf requests, where patches where you run transactions in parallel. You can then utilize the multi-core processor and use one core for each, which NSO will do if you do this in concurrently, and then you will concurrently go through the service and the validation stages, and then come to the critical section where the transactions will have to wait for each other, but so you want to minimize that, of course, by, for example, using commit queues, as we mentioned in the previous slide. Okay, let's go back to a dark place where NSO File.x was when it comes to performance, where transactions had to be done sequential, basically. At least service creation and validation had to be done sequentially, since the lock was taken before that instead of after this creation and validation. And then you had commit dry run and service check syncs that couldn't be done concurrently either, that can with NSO6. So there was much less gain of actually using multiple cores, where you would have one transaction per each core, and so dispatching that, because it would basically be the read write phase in the beginning where NSO would calculate the minimum diff that you would be able to parallelize, and then transaction lock would be taken, and you would have this long gray area here, transaction lock wait, before you could start with your service and validation code to run, which might take some time, and then commit to, for example, commit queues to do that. Say we have done our job here. We are uh, making several, doing several transactions in parallel, concurrently then. And we're using multiple cores, one, two, three in this case, with three transactions each. But we haven't turned on commit queues. What will happen then is that the config push to devices will be part of the critical section, which means that each transaction have to wait for the other. And this might take some time to push to device. So if the device is quite slow, this may take some time. These three devices are just as fast or slow, all of them. So it will take equal amount of time. But the critical section will remain, and the next transaction that we before was running concurrently will have to wait then for the first transaction, the second one, and the third one will have to wait for a second one, and so forth. Depends on where they are and who takes the lock first here. On the other hand, with commit queues, as soon as we have pushed to the commit queue and CDB, the lock will be released when we have commit queues, and the next transaction can continue with its critical section, and then so forth. So we'll save a lot of time here, especially if the device update is quite slow, which is often is the case. If it is, then you will have a lot of gain by using commit queues here. What we see here is a progress trace taken from a test run I did, where I was running two REST-conf edit transactions in parallel. And the way to visualize this, you can use the observability exporter, which has lots of features. This one here uses a very tiny Python script that just prints out the progress trace steps, which are all these steps here, and visualizes the trace ID with different colors, the transactions, which each gets its own trace ID with different colors. And these steps that you see here are the detailed steps. Well, this is actually the least detailed progress trace that you can have. You can have much more steps being included here in the progress trace. But these are the steps that I simplified in the previous slide when I showed the transaction manager. So here you have the REST-conf edit at the top. This is a span here, so this shows how long the REST-conf edit actually took for the two transactions. What you see down here is the service create, the create callback being called, and some Python code running. This was running for 3 seconds for each transaction, and here you can see how they are done in parallel, or concurrently, I would say. Same thing for the validation step here. The validation step is run for 3 seconds for both transactions being done concurrently. And then the commit to commit queues, which means that then for the device updates for the first transaction, it updates three. There's one device being updated per transaction. So here you have one, and next one that's been done concurrently as well. So all this will take 7.5 seconds. But if we look at here, where we baked the two transactions into one single transaction, now we have 13.5 seconds instead of 7.5 seconds. And the reason is that now we're not using the CPU cores in a multi-core processor for each transaction or each update of the device, but we're doing this one sequentially instead, where now this step here for create no longer takes 3 seconds, it takes 6 seconds. And so the validation step as well, that took 3 seconds being done concurrently for the two transactions, here now takes 6 seconds. And then we have the devices, even without the commit queue, being updated in parallel here or concurrently. But we saved a lot of time with by running two transactions concurrently instead of doing it then in one big chunk and not uh, doing any concurrency here between the transactions. So Nano services, if you look at them from a transaction performance use case, you might, if you looked at Nano services, you know that there's a Nano plan. In that plan, you have components. What's key here is that each component will run in its own process. So components run concurrently, and we will utilize that. In this example picture you have up here, there are states that we go through. There's always an init state. In this case, we have a T3 validated state for the transaction we were using before. We have a configured state. So what will happen here if we execute this component here with the plan we have implemented with states is that there will be post action. You can have post actions after or before. Then in this case, a create callback to a service. You can have several services. You can have pre conditions where you won't execute a state until the precondition is met and so forth. In this case, we keep it simple. We have one action being executed first in this validated state, where we can run some RFS validation code, for example. And then we have a configured state where we call the create callback that we, in this example service here, the RFS service, resource facing service. So this will be a resource facing normal service. And as I mentioned, then the benefit will be that we can have one transaction from a RESTconf, a CLI, commit, a netconf, edit config, instead of having to do the multiple RESTconf requests or edits with several transactions. We can just do one transaction to a Nano service, and the Nano service will take care of dividing it into components, or where each component for our service here will be represented by one service instance per device. So again, we will have one commit, and then that Nano service will take care of dividing this up into different components or processes, so the transactions can run in concurrently, as we saw in the previous slides. So now we can use a customer-facing service, where the customer-facing service might be just a container. It might be not being not caring so much about service instances, but it will do one transaction to update all the service instances, in this case 3 of them, in the resource facing service, where the Nano service then will take care of dividing these service instances into processes, one transaction each, and then run them concurrently, where the devices are then updated concurrently as well. When we have a customer-facing service, then we can have that running in its own node in a layered service architecture setup, an LSA setup, where we have one node with a customer-facing service, and then 2 or more nodes with a resource-facing service. Here in this picture, we have 2 resource-facing service nodes running NSO. Each of these running on its own processor. This is definitely multi-core processors. Here we're running 3 transactions in concurrently on each of these RFS nodes. So this means that the customer-facing service uses then layered service architecture to map its service to the RFS services on 2 different nodes here, and we have 6 devices being configured concurrently then. But you can imagine we can expand on this. We can have a multi-core processor here with 10 cores, Then we can run 10 transactions concurrently on each of these. And if we have then 10 nodes, 10 resource facing nodes with 10 transactions being running concurrently and updated devices concurrently, we can update 100 devices um, concurrently in this kind of setup, which will be a very powerful way of getting maximizing the performance and the wall clock time and throughput to update those devices then. So for further details, see the NSO example set. Here you have the examples NCS development guide concurrency model, where you have examples for each of these kind of variants that I show the performance um, transaction example, one for stacked services and one for LSA as well. And then also other things like retry of transactions is also there. So look into that. And then you have development guide chapters in the documentation, scale and performance optimization chapter, NSO concurrency model chapter. The Nano services chapter is also there if you want to look further into Nano services. The user guide has the commit queue chapter you can look into and for further details. And then we have the layered services architecture guide, of course.